If you're not into math, this video is for you. Hey everyone, I'm an undergraduate computer science and math student, and as you can probably imagine, every time I talk to my extended family on breaks, I always get the inevitable, "So how's college going? What are you studying?" And whenever I tell people I study math, I usually get the same kind of reaction. "Oh, I was never really good at math," or "I'm not really a math person." My general impression from these responses is that most people either don't really care about math, have an active distaste for math, or are curious about math but don't think they're cut out for it, which, as you might expect, I find to be really unfortunate because I think math is one of the coolest things ever. So recently, I've been thinking about ways to spark people's interest in math, and I thought it might be cool to try making a beginner-friendly guide to one of the most foundational and important fields of mathematics, known as set theory. I think set theory is a good entry point for beginners since it's relatively easy to understand the basics, and it also explains the why behind many of the concepts learned in high school math. Set theory is also completely different from the kind of math taught in high school, so I think it has potential to hook people in who may think in a more abstract way. So without further ado, let's get into it. I think the first natural question to ask here is, what is set theory? Well, it's the study of sets, which is probably pretty obvious. So the real first question we should ask is, what exactly is a set? To put it simply, a set is a collection of things. These things can be literally anything. They can be numbers, letters, or even VTubers. But how do we represent sets mathematically? Well, in math, we represent sets using curly braces and putting the things inside of the set inside the curly braces, separated by commas. I've been referring to the things inside of sets as things so far, but the technical term for them is elements. So we would say that 1, 2, and 3 are elements of this set. We also have a symbol in set theory that means that the thing on the left is an element of the set on the right, and it sort of looks like a weird curvy E. If we want to say that the thing on the left is not an element of the set on the right, we simply draw a line through the symbol. Now, there are a few extra details about sets that we need to consider. The first is that sets cannot contain duplicate elements. So for example, this collection here is not a set because it contains 2 ones. The next thing we need to consider is that sets are unordered. So no matter how we arrange the elements within a set, the set remains the same. As an example, the set containing 1, 3, and 2 in that order is equal to the set containing 1, 2, and 3 in that order, since order does not matter with sets. This leads us very nicely into the definition of set equality. A set A is equal to a set B if A contains the same elements as B. As another quick example, these 2 sets of colors are equal because they both contain the same colors. Now that we understand what sets are, what are some examples of sets that mathematicians commonly use? Well, as you might expect, we often work with sets of numbers in math. One of the most basic sets of numbers we use is the set of natural numbers, which is represented by this fancy n. This set simply contains 0 and all of the positive whole numbers. Something I'd like to point out here is that since there are an infinite amount of positive whole numbers, the number of elements in this set is infinite, and that's completely okay. We're allowed to put infinite elements into a set. It turns out that we can actually extend the natural numbers to a new set called the integers, which is represented by a fancy z. The set of integers is just the set of natural numbers as well as all of the negative whole numbers. We can then extend the integers to the set of rational numbers represented by a fancy q. Notice here that the way this set is represented is different from the others, and that's because this set is written using set builder notation. Set builder notation is a way to describe what kinds of elements are in the set without having to actually write them out. Essentially how this works is that the part on the left side of the colon describes what the elements in the set look like, and the part on the right side of the colon describes what rules these elements must follow. And the colon just means such that. So if we were to read this in plain English, it would read, all of the fractions such that m and n are integers, and n is not equal to 0. The reason n isn't allowed to equal 0 is because we cannot divide by 0. So the rational numbers are just the fractions with integers as the numerator and denominator, where the denominator is not 0. Next, we have what is arguably the most frequently used set of numbers, called the real numbers. I'm not going to write out how to construct the real numbers, since it's a bit complicated and outside the scope of this video, but to explain it simply, the real numbers are the rational numbers, as well as all of the numbers with an infinite amount of numbers after the decimal point, where these numbers don't fall into a repeating pattern. These other numbers are called the irrational numbers. It turns out that we can keep extending numbers after the real numbers, but these extensions are much more rarely used. Now that we've gone over some examples, what can we actually do with sets? One thing we can do is take their cardinality. The cardinality of a set A is the number of elements in A. We represent the cardinality of a set A by putting vertical bars around the set like so. As an example, what is the cardinality of the set containing 1, 2, and 3? Well, since there are 3 elements in the set, the cardinality is simply 3. Now, what about this set? Well, there are 4 elements in the set, so the cardinality is 4. So, finding the cardinality of a set is super easy, right? Well, it is for sets containing finite elements, but things get dicey when we want to take the cardinality of infinite sets. So let's do just that. What is the cardinality of the set of natural numbers? Infinity, perhaps? Not quite. The natural numbers do contain an infinite amount of elements. However, something you may not know is that there are actually different sizes of infinity. The classic way to understand this as a beginner is to understand Cantor's diagonal argument. But before we get into that, let's consider when the cardinality of 2 sets is the same. Let's say that we have these 2 sets here. Do these 2 sets have the same cardinality? Well, one way you could determine this is by counting up the elements in both sets and seeing if that number is the same. However, I want you to think about this from a different perspective. This new perspective is going to involve functions, but not in the way you're probably used to seeing them. Typically, the way functions are described in high school is something that takes an input and returns an output. This is a pretty good understanding of what a function is, but most people don't realize that sets are actually involved here. A function is actually a mapping from one set to another. In other words, it takes elements in one set and associates them with elements in another set. So in this example, this particular function maps 1 to red, 2 to blue, and 3 to yellow. To introduce some terminology you might be familiar with, the set we're mapping from is called the domain of the function, and the set we're mapping to is called the codomain of the function. Most people have probably heard of the domain before, but most people are probably unfamiliar with the term codomain. However, the codomain is similar to a term people probably know, which is the range of a function. The range of a function is simply the elements in the codomain that actually get mapped to. To understand the difference between the range and the codomain, consider this example. What is the codomain of this function? Well, it's just the entire set we're mapping to. Okay then, what's the range? Well, the range is the set of elements that actually get mapped to in the codomain. So, since there are arrows pointing to red, green, and blue, red, green, and blue are in the range. However, since yellow has no arrow pointing to it, meaning it doesn't get mapped to, it's not in the range. So the range of this particular function is the set containing red, green, and blue. Next, we need to learn about 2 types of functions: injective functions and surjective functions. These terms might sound scary, but they're not, I promise. An injective function is just a function where each element in the domain maps to a unique element in the codomain. What I mean by unique here is that no other element in the domain maps to that same element. As an example to clear up any confusion, let's look at an example of an injective function. So, why is this function injective? Well, 1 maps to red, which no other element maps to, 2 maps to green, which no other element maps to, and 3 maps to blue, which no other element maps to. So each element in the domain maps to its own unique element in the codomain, which is what an injective function is. Now let's look at a function that is not injective. this function is not injective because both 1 and 2 map to the same element, which is red in this case. Next, let's talk about surjective functions. A function is surjective if every element in the codomain gets mapped to by an element in the domain. To use the terminology we discussed earlier, a function is surjective if the range of the function is equal to the codomain of the function. Let's look at an example of a surjective function. As you can see, every element in the codomain has an arrow pointing to it, so the range is equal to the codomain, which means the function is surjective. Now let's look at a function that is not surjective. Notice here that blue does not get mapped to, so the range does not include blue, which means the range and the codomain are not equal, so this function cannot be surjective. Great, so what does this have to do with cardinality? Well, there are some facts about injective and surjective functions that can tell us about the difference in cardinality between two sets. Firstly, an injective function between two sets exists only if the cardinality of the domain is less than or equal to the cardinality of the codomain. Why is this the case? Well, let's look at an example where the cardinality of the domain is greater than the cardinality of the codomain, and let's try as hard as we can to make an injective function. Alright, so we want to map each element in the domain to its own unique element in the codomain. So let's map 1 to red, and then we need to map 2 to something else, so let's map it to blue. Now we need to map 3 to something other than red or blue since they're already mapped to, so let's map it to green. But now what do we do with 4? Any element we map 4 to will make the function not injective, since 4 and some other number will map to the same element. So as you can see, when the cardinality of the domain is larger than the cardinality of the codomain, there aren't enough elements in the codomain for each element of our domain to get its own unique element in the codomain. This concept is known as the pigeonhole principle. Now, why are we guaranteed an injective function if the cardinality of the domain is less than or equal to the cardinality of the codomain? Well, because now there are either exactly enough elements or more than enough elements in the codomain to pair up our elements in the domain with. Great, let's put that fact on hold for a second. The second fact I want to discuss relates cardinality to surjective functions. A surjective function between two sets only exists if the cardinality of the domain is greater than or equal to the cardinality of the codomain. Now, why is this the case? Well, let's look at an example where the cardinality of the domain is less than the cardinality of the codomain. Remember that in order for a function to be surjective, every element in the codomain must get mapped to by an element in the domain. So let's try to make a surjective function between these two sets. Let's map 1 to red, 2 to blue, and 3 to green. Well, now what? We've run out of elements in the domain to map from, so no matter how we map the elements in the domain here, one element in the codomain will always be left uncovered. So when the cardinality of the domain is less than the cardinality of the codomain, we cannot make a surjective function between them. However, we are guaranteed to be able to make a surjective function if the cardinality of the domain is greater than or equal to the cardinality of the codomain, since we now have exactly enough or more than enough elements to cover the codomain. Okay, that was a lot, but it's about a payoff. We know that an injective function only exists between two sets when the cardinality of the domain is less than or equal to the cardinality of the codomain, and we know that a surjective function only exists between two sets when the cardinality of the domain is greater than or equal to the cardinality of the codomain. So ask yourself this: when can there exist an injective function and a surjective function between two sets at the same time? Well, when the cardinalities of the two sets are equal, right? If the domain has greater cardinality, then there are no injective functions, and if the domain has a lower cardinality, then there are no surjective functions. But if the cardinalities are equal, then there exists an injective function and a surjective function between them. And not only that, there exists a function between them that is both injective and surjective at the same time. A function that is injective and surjective is called bijective. A more intuitive way to think about this would be to think of a bijective function as a function that pairs up elements between the two sets. We can now say when the cardinality of two sets is equal. The cardinality of two sets is equal if there exists a bijective function between them. Equipped with this knowledge, we can now tackle Cantor's diagonal argument. The goal of Cantor's diagonal argument is to show that there is no bijective function from the set of natural numbers to the set of real numbers between 0 and 1. To begin, let's line up all of the natural numbers in a column on the left. Next, let's generate a list of real numbers between 0 and 1 and pair them up with the natural numbers. Now what we're going to do is show that no matter what list we generated, we can generate a new real number between 0 and 1 that is not contained in the list. And since all of the natural numbers are already paired up, we will not be able to pair up this new real number with a natural number, meaning we cannot construct a bijective function between the natural numbers and the real numbers between 0 and 1. Based on what we just talked about, this also means that the set of natural numbers and the set of real numbers between 0 and 1 have different cardinalities, even though they both have infinitely many elements. So how exactly do we generate a number that is not contained in this list? Well, this is where the diagonal part of Cantor's diagonal argument comes in. Let's just focus on the digits along the diagonal in our list. What we're going to do is move down the diagonal, add 1 to each digit, and then insert these into our new number. The only exception is if the digit is a 9. If we get a 9, we'll just roll it back over to a 0. So the first digit in the diagonal is 5, so we're going to add 1, which gives us 6, and then make that the first digit after the decimal point in our new number. The next diagonal digit is a 1, so we'll add 1, which gives us 2, and then insert this as the second digit in our new number. The next two diagonal digits are also 1, so we'll do the same for those as well. Okay, now we have a 9, so in this case we need to roll this back to a 0 and then insert it into our new number. Next, we have a 4, so we add 1, which gives us 5, and then insert it like the others. Then we continue this process for all of the numbers in our list. This process clearly gives us a new real number between 0 and 1, but how do we know that it's not in the list? Well, this new number is different from the first number in the list at the first digit, the second number in the list at the second digit, the third number in the list at the third digit, and so on. So the new number we just generated is different from every number in our list at least one digit, which means it cannot possibly be in the list. And the key here is that no matter how we create our list, we can always construct a number that is not in it. Since we already paired up all of the natural numbers with real numbers in the list, we cannot pair up our new real number with any of the naturals, which means we cannot construct a bijective function between the naturals and the reals between 0 and 1. So, the cardinality of the set of natural numbers is different from the cardinality of the set of real numbers from 0 to 1, even though they both contain infinite elements. And there are actually more elements in the set of real numbers from 0 to 1. So how exactly do we describe cardinalities of sets with infinite elements then? Well, we use what are called Aleph numbers. For example, the cardinality of the set of natural numbers is Aleph 0, which is the smallest infinity. The next biggest infinity is Aleph 1, then Aleph 2, and so on. Now, you may be asking, well, what's the cardinality of the set of real numbers from 0 to 1? And that's a great question. While we know that it's bigger than Aleph 0, we don't actually know exactly which Aleph number it is. There is a hypothesis called the continuum hypothesis that says that the cardinality of this set of reals is Aleph 1, but we don't know whether this is true or not. And it turns out that it is actually impossible to prove or disprove the continuum hypothesis at all, which was proven by Kurt Gödel and Paul Cohen. To give you a couple more examples of cardinalities of infinite sets, the cardinality of the set of integers and the set of rationals is also Aleph 0. For the final section of this video, I want to focus on some other basic operations we can do on sets and other miscellaneous concepts. First, let's talk about subsets. A set A is a subset of a set B if all of the elements in A are also in B. As an example, the set containing 1 and 2 is a subset of the set containing 1, 2, and 3, since 1 and 2 are both in that set. This sideways U symbol is the symbol we use to say that the set on the left is a subset of the set on the right. Notice that the set on the right is not a subset of the set on the left, since the element 3 is not contained in the set on the left. We call a subset of another set a proper subset if it is not equal to the other set. So, as an example, the set containing 1 and 2 is a proper subset of the set containing 1, 2, and 3. A couple facts that are important to remember about subsets are that every set is a subset of itself, and the empty set is a subset of every set, where the empty set is the set that contains no elements. Note here that the empty set is typically represented using this circle with a line through it. Next, let's talk about power sets. The power set of a set A is the set of all subsets of A. The shorthand way we represent the power set is by using this fancy P symbol and putting the set in parentheses after the P. As an example, let's find the power set of the set containing 1 and 2. As we just discussed, the empty set is a subset of every set, so the power set will contain the empty set. Next, we have the set that just contains 1, we also have the set that just contains 2, and lastly, we have the set itself. These are all possible subsets of the set containing 1 and 2, so this is the power set. An important fact to remember about power sets is that the cardinality of the power set of a set A is 2 to the power of the cardinality of A. Let's see if this is true for the example we just looked at. The cardinality of the set containing 1 and 2 is 2. And the cardinality of the power set of this set is 4, which is 2 to the power of the cardinality of the set, 2, which is exactly what we expect. This rule also applies to infinite cardinalities, so we can say that the cardinality of the power set of the natural numbers is 2 to the power of aleph is 0. Now, let's talk about the union of two sets. The union of two sets A and B is the set containing all of the elements in either A or B. So, as an example, the union of the set containing 1 and 2 and the set containing 3 and 4 is the set containing 1, 2, 3, and 4. It is important to point out that if both sets contain a particular element, that element only appears once in the union, since sets do not contain duplicates. So, for example, the union of the set containing 1 and 2 and the set containing 2 and 3 is the set containing 1, 2, and 3. Notice that we use this U symbol to mean take the union of these two sets. Lastly, let's talk about the intersection of two sets. The intersection of two sets A and B is the set containing the elements that A and B have in common. So, as an example, the intersection of the set containing 1 and 2 and the set containing 2 and 3 is the set containing just 2. We call two sets disjoint if their intersection is the empty set. In other words, if the two sets do not share any elements in common. Notice that we use an upside down U symbol to mean take the intersection of these two sets. I hope you were able to get something out of this video. My hope is that after seeing this kind of abstract mathematics, you are interested to learn more about math and come away with a new appreciation for the subject. Set theory goes much, much deeper than this, but this video gives a good overview of the basics and the idea behind the field. I spent a lot of time working on this video, so please consider liking and subscribing on your way out if you made it this far. Thanks for watching.